Hello everyone, today we are going to discuss a very important book, that is William Carruthers. So we will discuss all the examples of chapter number 1 first of all. So this book is very important as far as the CSIR net GATE exam, then JAM exam, joint admission test, JAM exam, then set exams, any set exam you take. These examples, examples of this book is very important. So as far as my knowledge is concerned, this is very important book, and we need to solve the examples of this particular book. So today we will discuss the chapter number 1 examples, some of the examples of chapter number 1. So this is a huge series. I will cover the examples of this particular book. So please do like, share, subscribe to my channel, and please share this video to your friends so that also they will also get the knowledge about the chemistry. Okay. So first of all we need to understand that what is meant by acid. Acids are proton donors. Acids are proton donors. Okay. What is meant by base? Generally bases are proton abstractors. Generally protons are proton abstractors. Okay. Now all organic acids are weak acids. Okay. Do remember this particular point. So one more point that you need to understand, that acidity is inversely proportional to the pKa values, and directly proportional to the acidity is directly proportional to the Ka values. Okay, you need to understand this particular point. So as the pK value increases, acidity decreases, and as the acidity increases, pK value also decreases. So as the Ka value increases, acidity increases, and as the acidity decreases, Ka value also decreases. So here they have mentioned some compounds, some acids and some compounds, and along with the compounds their pK values they have mentioned. Okay, now understand that this is acetic acid, this is first one is acetic acid, and acetic acid having value pK value 5. Okay, as the pK value decreases, acidity increases. Okay, now you need to understand that here in this case pK value is 5. Okay, that means this is more acidic than this particular compound. Okay, so this nitrile substituted ester, this is nitrile substituted ester, or we can call it as a active methylene compound. So second one is active methylene compound having pK value about 9. Then this is also active methylene compound, and pK value about 9. Now next one is nitromethane. So this carbon having 3 hydrogens, and these 3 hydrogens having acidic characters, and acidity of this particular hydrogens are about 10. Okay, so as the pK value increases, acidity decreases. As the acidity increases, pK value decreases. Or you can think like that, that as the pK value decreases, acidity increases. Okay, So this is also active methylene compound. Fifth one is also active methylene compound having acid having pK value 11. So this is also sixth one is a active methylene compound having acidity having pK value 13. That means this compound having more acidity. This compound is more acidic than this particular compound. Okay. Now comes methanol. Methanol is a polar molecule, you know it very well. Exceptionally high polar molecule. This is high this possesses high dipole moment. It is just because of percentage S character. Okay, high percentage S character. Okay, so this is highly polar molecule having acidity value. Methanol having acidity or pK value 16. This is a substituted acid. Okay, so this is acid, carboxylic acid. Okay, substituted, that is this compound C double bond O OH, that is pyruvic acid. So pyruvic acid having pK value 19. Okay, so this is a less acidic as compared to this methanol, though it is this is not a pyruvic acid. This is not a pyruvic acid. This is aldehyde molecule. So this is not a pyruvic acid. Sorry, this is not a pyruvic acid. This is a aldehyde molecule. Okay, this is the aldehyde molecule. Understanding? Got the point? Okay. Now you need to understand that. So that you will. So you need to understand that as the pK value increases. What I exactly want to tell you is that as the pKa value increases, acidity decreases. Okay, so these are the compounds which are having their pK values, okay, along with their pK values that we need to understand. Okay, so this table is very important. Which will help us to determine the acidity, or which will help us in the enolate chemistry as well. Okay, so this is the active methylene compound. Active methylene compound. Okay, this is active methylene compound that we. Okay, this is the substrate which is having active methylene group. Okay, substrate having active methylene group. So if you add base, what will happen? These are having protons. Okay, these are having protons. It will take proton and there is a formation of anion over here like this. Okay, these anion will do the conjugation and there is a formation of this. Okay, if this anion when does the resonance, then there is a formation of this particular canonical structure of this particular first molecule is second, and canonical structure of this particular, if you do the further conjugation like this and like this, then again third structure here generates. Okay, third structure found over here. Okay, so this active methylene compound is very important as far as synthesis is concerned. Okay, so this is nothing but the enolate anion. Okay, if you provide base to this particular active methylene compound, base will abstract proton and there is a formation of enolate anion. Okay, let us discuss the mechanism of this particular active methylene compound. So what is the active methylene compound? This is the active methylene compound. C double bond O OET, C double bond O OET. Okay, this is the active methylene compound having two hydrogens. Okay, having two hydrogens which are acidic in nature. If I provide base, what it will do? It will take the proton, and there is a formation of anion over here. Okay, when there is a formation of anion over here, when there is a formation of anion over here on this carbon system, why there is a formation of anion? It is just because of whatever the anion which is generated over here, whatever the anion which is generated over this carbon, this is much more stable over here. That is why this base easily abstract this particular proton. Okay, so this base can do the conjugation. Okay, when this base do conjugation like this, this negative charge will move further like this, and this pi bond will break, and there is a formation of this particular compound like this, O minus OET, C double bond OET, like this. Okay, so here reversible reaction, this is the reversible reaction, because whatever the enolate anion which is generated over here, it can do the conjugation, and again it can take the proton from the generated conjugate acid. Okay, so that is why this is very, very important reaction that we need to understand. So when we provide active methylene compound when treated with a base, there is a formation of enolate anion. This is what we need to understand over here. Okay, so if again when this charge moves like this, when you do the conjugation like this, when you do the conjugation like this, another canonical structure generates in the reaction, OET, C double bond O minus OET. Okay, so another substrate is generated over here, another canonical structure generated over here. So this is the first canonical structure, so this is the first, this is second, and this is third. Okay, so now this mechanism is completed over here. Now the enol, now we have generated enol system over here. Now these enolates, when these enolates when we treat with alkyl halides, when these types of enolate, OET, double bond O minus OET, when these type of enolates, when we treat with the alkyl halides, so X is equal to bromine, it can be chlorine or iodine, okay, which is good leaving group. So when we do the reaction of these enolate anion with the alkyl halide, so this is alkyl halide, what will happen? Simply substitution reaction will happen like this. How? Now this charge can come back like this, whatever the negative charge which is generated on this particular oxygen, it can come back like this, and this is going to attack on the electrophilic center, because of this is more electronegative element. Okay, this will pull electron towards itself. There is a formation of minus del charge over here and del plus charge over here on this particular carbon system. Okay, so this carbon is electrophilic in nature. Why? It is just because of electronegativity difference between this carbon and this particular halogen system. Okay, so this is a leaving group, this is leaving group, this is leaving group. Okay, and having more electronegative, okay, more electronegativity, due to which partial charges will develop on the adjacent carbon. It will carry del minus, it will pull electron towards itself like this. When it pull electron towards itself, there is a formation of del minus charge on the halogen and del positive charge on the carbon system. Now in such a way that when we treat this enolate anion to this particular electrophilic alkyl halide, what will happen? This charge can come back like this, and this will attack on this particular electrophilic center, and this halide, this halogen will leave out from the reaction with bonding electrons. Okay, so it will leave out from the reaction, and there is a formation of this particular product over here. There is a formation of this particular product over here like this. That is this particular product. Okay, so this is the a reaction. This is the reaction of active methylene compound, active methylene compound. This is the reaction of active methylene compound with alkyl halides in the presence of base. Okay, in the presence of base. So there is a formation of substituted this methylene compound, substituted methylene compound. Okay, substituted methylene compound. Are you understanding my point? Now let us discuss the next reaction. Okay, now they have given here, here they have mentioned one reaction based on the carbon-carbon bond formation reaction. So all we are discussing here in this chapter, all the examples, whatever we are discussing in this particular chapter, that is based on the carbon-carbon bond formation reaction. Okay, now let us discuss this particular reaction. So here they have mentioned one ketone. Okay, one ketone they have mentioned here, and this ketone having alpha carbon, and this alpha carbon having two hydrogens. Okay, so when we treat this compound with base, with this particular base, so bases are proton abstractors. Bases are proton abstractors. Bases are proton abstractors. Okay, base, what it will do? It will simply take the proton. It will attack on the proton, and this proton, it will take the proton, and whatever the bond between carbon and hydrogen is there, that will break, and there is a formation of anion over here. So this anion delocalize, because whenever there is a negative charge, sigma bond and pi bond, we already discussed and we already studied that in the general organic chemistry. We already discussed in the general organic chemistry that whenever there is a negative charge on this particular carbon, okay, lone pair pi double bond, okay, lone pair single bond and double bond. So conjugation is there, so it will do the conjugation like this, and there is a formation of negative charge on this particular oxygen like this. Okay, oxygen like this. This oxygen will carry negative charge like this. Okay, this oxygen will carry negative charge like this. So this is nothing but the enolate ion. Okay, this is nothing but the enolate ion. Okay, so this is unstable. This is unstable. Okay, when we treat with the again alkyl halide, when this enolate anion we treat with alkyl halide, when we treat with alkyl halide, what will happen? When treat with alkyl halide, what will happen? This enolate will come back like this. This anion will come back like this. So this is act as a nucleophile. This is act as a nucleophile, and this carbon act as a electrophile. Simply nucleophile electrophile will interact each other. Okay, and there is a formation of reaction, that is carbon-carbon bond formation reaction will take place. So this anion can come back like this, and this is act as a nucleophile. So this bond will break, and it is going to attack on this particular electrophilic center, and this bond will break, and there is a formation of new carbon-carbon bond formation like this. Okay, there is a formation of new carbon-carbon bond. Okay, so this is a hydrogen, and this is also hydrogen. So this is a hydrogen, this is also hydrogen. Okay, now this is our alkyl group, this carbon and this carbon having these two hydrogens. This is our product. This is our product. This is our substituted product. So this is our final product. Okay, so let us discuss the next example. Let us discuss the next example. Here also, this is nothing but the enolization mechanism. Okay, this is nothing but the enolization reaction. So this is nothing but the enolization reaction. Okay, they have mentioned the new reaction, that is enolization reaction. Enolization reaction. So this is nothing but the enolization reaction. So in the book further they have mentioned enolization reaction. So this is enolization reaction. How enolization takes place? In the presence of acid as well as in the presence of base, enolization takes place. In the presence of base, enolization takes place. Okay, or in the presence of base, enolization takes place like this. Now let us discuss the mechanism. So this is the carbonyl compound. This is the carbonyl compound having alpha hydrogens. Now we already discussed this when treated with the when we treat with this acid in the presence of acid, what will happen? In the presence of acid, what will happen? These non-bonding electrons will take the proton. This non-bonding electron will take the proton like this, and when it takes proton from the acidic medium, what will happen? Electrophilicity of this particular carbonyl carbon increases. Electrophilicity of this particular electrophilicity of carbonyl carbon increases. When electrophilicity of this particular carbonyl carbon increases, what will happen? Now this bond will break like this, and this bond will break like this, and there is a formation of new pi bond, and this pi bond will open up like this, and there is a formation of R double bond single bond R. This is single bond, one new pi bond generated over here. This alkyl substitute, this alkyl group is as it is here, and there is a formation of OH like this. So here it is called as enol form. So enols are generated in this particular enol when it is generated in the presence of acid. In the presence of acid, enolization will take place. So this is the mechanism of enolization. So this is the mechanism of enolization that we have to understand. Next reaction is now these enolates. Now these enols and enolate, when we treat with the, now again one important reaction is mentioned in the book. We will discuss this. First of all we will discuss this, then we will discuss next examples. So in this book they have given this particular actimethylene compound, what we already discussed. So this reaction we already discussed. We have generated the mechanism of this particular reaction. We already discussed. Let us discuss once again the mechanism of this particular let us discuss once again the mechanism of this particular actimethylene compound. So this is the actimethylene compound. OET. In the presence of base, what will happen? In the presence of base, this is the proton. Okay, this is the alpha carbon, or this is the actimethylene group. Okay, this is the methylene group having two protons which are acidic in nature. So what it will do, simply the base will take the proton, and there is a formation of anion system over here, like this. OET, C double bond O, OET. There is a formation of anion like this. So this anion is much more stable, that is why this reaction is happening over here. Okay, and formation of BH takes place. So okay, so this must be weak acid. Okay, this must be weak acid. Okay, then and then only these are good enolates. So this is enolate. This is the enolate. Okay, this is the mechanism of this particular reaction 1.4. Okay, 1.4 reaction we have discussed now. Okay, now these enolate we need to treat with the alkyl halides or electrophilic centers. Now here new reaction is present. Here new reaction is present, that is Mitsunobu reaction. So Mitsunobu reaction is a reaction in which new carbon-carbon bond formation takes place. So this is the Sn2 reaction. This is Sn2 reaction. This is Sn2 reaction. Okay, substitution, nucleophilic, substitution nucleophilic, bimolecular, substitution nucleophilic, bimolecular, Sn2 reaction. Here carbocation will not form. Carbocation will not form at all. Here carbocation will not form at all. Okay, this reaction takes place through transition state. This reaction takes place to transition state. Rate is directly proportional to the substrate as well as substrate plus nucleophile. So order of reaction is 2. Okay, order of reaction is 2. Okay, carbocation will not form, and rate is directly proportional to, again rate is directly proportional to the less steric hindrance, less steric of substrate. Okay, and rate is inversely proportional to the steric hindrance. As the steric hindrance increases, rate of the reaction decreases. Okay, so this is the Sn2 reaction. Okay, so this is the given by the scientist. So this reaction has been predicted by the scientist Mitsunobu reaction. Okay, so this is the Sn2 reaction. Okay, so let us discuss the mechanism of this particular reaction. So what they have mentioned? They have mentioned substrate. COOET, and here S double bond O, and R is there. Okay, R is there. So this is the substrate. That we need to understand. Okay, here substrate is this. Here between this oxygen is present over here. So this is sulfone group and this is ester. Okay, alpha. Okay, so this is the reaction that we need to understand now. Okay, so here ester group is present over here. So this is the ester group. And to this ester group, further alpha carbon is present over here, and this alpha carbon contains sulfone group. Okay, sulfonyl group. Okay, so this is what the reaction is, and this present. Okay, this connected with the dash bond over here. Okay, so this becomes away from the observer. So this is away from the observer. So incoming nucleophile will attack from the opposite side of this particular reaction. That we need to understand. Okay, opposite from this particular substrate. Okay, opposite from this particular substrate. So when this molecule, when we treat with this particular active methylene compound in the presence of base, in the presence of base, in the presence of base. Okay, in the presence of base. Okay, so step 1 is, so this is the reaction. When we do the reaction, so this is the reaction. So this is what the reaction is. Okay, when we treat this particular compound with this molecule or with this particular reagent, and here some reaction condition is there, reaction condition. So this is the reaction condition, base is present, and this is active methylene compound. Okay, active methylene compound. So this is the reaction. We need to find out the product. So this is the Sn2 reaction. Okay, so in the first steps we need to product we need to find out. Okay, so the step 1 is mechanism. Let us discuss the mechanism. Let us discuss the mechanism. So step 1 is this. Step 1 is this. So this is the dash bond away from the observer. Oh yes, double bond O. This is methyl. Okay, this R is equal to methyl. Okay, this R is equal to methyl. Here, okay, first of all this is act as a substrate. So this carbon act as an electrophile. Okay, I will take letter I will take this. First of all I will take this active methylene compound. When this active methylene compound treated with base, when we treat with the base will abstract proton like this, and there is a formation of enolate anion. OET, O minus, double bond, OET. Okay, so this is the enolate anion. When this enolate anion, okay, this enolate anion, this O minus, OET, C double bond O, OET. So this enolate anion, when we treat with this particular compound, COOR, okay, and here dash bond is present over here. O yes, double bond O, methyl system. Okay, methyl system is there. Okay, COOET. We will take this R is equal to here. This R is equal to ET. Okay, ethyl. Okay, so let us discuss that. So this is away from the observer. This bond is present. Okay, this carbon, this is the alpha carbon, and this is away from the observer. This bond is, okay, present away from the observer. So this group is away from the observer here. Okay, now exactly opposite to this particular substrate, opposite to this particular group, one sigma star orbital is present over here. So this is the sigma star orbital. Now what will happen? This enolate anion, this anion will come back like this, and this will attack exactly opposite to this particular group like this, and this will leave out with the bonding electron. Okay, this will leave out from the reaction. This is very good leaving group. So this is leaving group, good leaving group. Sulfones are highly, good leaving group, best leaving groups. So minus O double bond, yes, double bond O, it will leave out from the reaction, and here this active methylene compound. So the bond between this particular active methylene carbon and this particular alpha carbon here, formation of new bond takes place over here like this. Okay, now what is the product? So product is this C double bond O, OET. Okay, OET. Now this is the actylmethylene compound. This is the actylmethylene compound, COOET, COOET. Okay, since it has been attacked on this particular sigma star orbital of this particular sulfone group, what will happen? So it has been attacked on this particular carbon from the opposite stereochemistry of this particular group. Okay, so it will attack from, so it will do the, so it has been attacked from the opposite side of this particular leaving group. So this becomes wedge, so it will attack from the front side. So it will attack from the front side. So the stereochemistry of this particular incoming group will be the opposite to this particular sulfone. So this is our final product. So this is our final product, and this reaction is known as Mitsunobu reaction. So this is the mechanism. This is the mechanism of this particular reaction. Okay. Now, next reaction that we need to understand. Okay. Next reaction here is very, very important. When these enolate anion, when we treat, again same enolate anion we have used here. When these enolate anion, when we treat with this particular substrate, what will happen? This anion can come back like this, and this will attack either on this particular sigma star orbital, or it can attack at the pi star orbital of this particular sp2 center. Okay, so here mixture of product takes place, that is A and B. So this one is a major one. So this is a major one because this alkene is more substituted. So this alkene is more substituted. Okay, more substituted alkene. More substituted alkene is more stable. So this is a less substituted alkene is less stable. Okay, why it is so? It is just because of count the hydrogens. Okay, count the hydrogens, hyperconjugation. Okay, count the alpha hydrogens, and that alpha hydrogens, if number of alpha hydrogens are more, then that structure becomes more stable. Here only one alpha hydrogen is present, and here there are 1, 2, 3, 4 hydrogens are present. So this is the, here more alpha hydrogens are present. That is why it has more hyperconjugative structures. Here less hyperconjugated structure, that is why it is less stable, it is more stable. So more substituted alkene is more stable, and less substituted alkene is less stable. That is why it will form majorly. Okay, so it can attack. So this enolate anion can come and it can attack on the sigma star orbital of this particular carbon chlorine bond, or it can attack on this particular pi star orbital of this particular sp2 center or alkene system, and this can move like this, and this can goes out from the reaction like this. Okay, when this enolate anion attacked on this particular electrophilic center, it can leave out from the reaction, and there is a formation of this particular product. If this enolate anion attacks on the sp2 center, pi star orbital of the sp2 center, then this can move and this can goes out from the reaction, and there is a formation of more substituted product. Okay, let us discuss the mechanism of this particular mechanism of this particular reaction. Okay, let us discuss the detailed mechanism of this particular reaction. So this is our substrate. Okay, this is our substrate. Okay, this is our substrate. Mechanism. Okay, this is our substrate. This is our substrate. When we treat with actylmethylene compound, active methylene compound O minus OET, C double bond O, OET. Okay, so first possibility is it can attack on this sigma star orbital of this particular carbon chlorine bond. Okay, so it can come back like this and it will attack on this sigma star orbital, and this will leave out from the reaction, and there is a formation of this particular compound. There is a formation of this particular compound, COET, OET. So this is the A product, less substituted one. Okay, so this pathway, this is the A pathway. Now B pathway is, so this is our substrate, okay. When this substrate, when we treat with active methylene compound, so I can generate this structure also, OET, active methylene compound. What will happen? This will come back like this. Okay, what will happen? This will come back like this, and this is going to attack on the pi star orbital. So these are having pi star orbital, these are pi orbital. Okay, these are having pi star orbital, and when it attack on the pi star orbital, these will move, this pi bond will move, and this will leave out from the reaction. This will leave out from the reaction, because this is good leaving group. This is good leaving group. Okay, so what is the product? This will be the product, double bond. This will be the product, C double bond O, OET, C double bond O, OET. Okay, this is the final product of this particular reaction. So this is more substituted product. So this is the more substituted product, and this is the major product. So here mixture of product takes place. Okay, so we will stop here.